So I want to make this video to catch you guys up with what's going on. If you saw my last video, I went over our different stock mount intercooler options and my plan to create my own, essentially. So if you missed that, go ahead and go back and watch that if you're interested. I kind of went down a rabbit hole. I didn't want to spend a ton of money on some intercoolers I saw some faults with, so decided to design my own and go down that route. So full disclosure, I'm a lot further in the process than what the videos actually show. I haven't had time to edit videos and whatnot. So today I'm going to go over the CFD analysis I did with the different intercooler cores. My prototype is actually welded up and ready to put in the car. I'm just currently working through creating the duct. Here you got the factory duct, and you see it's pretty complicated. So I have to essentially recreate this with this aspect mounting to my much larger intercooler. So it's going to be very similar to the other air ducts offered with the Australian ones, but that's something I have to design and fit to my particular intercooler core. So that's one thing I'm doing. I still need to design a AST relocation and a couple brackets, but as far as the intercooler, it is complete, and I'm going to reveal that in some future episodes. But let's get to the CFD analysis. Essentially what I did was I took a bunch of pictures, as many pictures as I could find, like what I showed with the last video, uploaded them into CAD. I took the dimensions I knew of the cores. You can put that into CAD and essentially create the size. So I got the dimensions as close as I could without having an actual unit in my hands. I recreated the end tanks. For CFD, I only ran the hot side core because that's the core I'm really worried about. The top tank design on the core, if you missed it, it tapers down on one side of the core to allow the cold side outlet of the front core to pass over it. So to me, that's a restriction and doesn't allow enough airflow to go through the core. You don't fully utilize that rear core, so you're really only using half to 3/4 of the rear core, and you could be a lot more efficient doing something else, which I designed and I'm going to try to implement. Only time will tell how well it works, but I'm excited with the progress I've made already. So with the CFD analysis, I ran a whole bunch of different tests. I ran everything from 50 CFM all the way to 1,000 CFM, and really the results didn't change. So they all flowed, the air particles flowed the same way. I went from 8 PSI to 25 PSI, and again, there's no difference with where the air particles went. I believe the conditions that I ran these tests I'm about to show you were done at 600 CFM under 20 pounds. So all of them that I'm showing you were under the same exact conditions within the CFD environment. I only modeled one Australian version because those two intercoolers are so similar in dimensions. Really the only difference is that it looks like they use the same exact core diameters, and they may even use the same exact cores. I don't know, but the dimensions of them are identical. The only thing that different that I found is you'll see in the previous video I made was the end tank design. So one of them has a cast end tank, which is a lot more smooth. That would be my preference to have that. And the other one is hand-shaped sheet metal. So, but as far as the flow, they should be very similar. So I only modeled one of those for us to analyze. So let's get to the results. The first intercooler I tested was the Night Sports. Here you can see the shape of the top tank design. You have flat cut tank pieces here. There's no smooth transition. Looking at the airflow here, you can kind of see where that's at there, but this pretty much confirmed my hunch. You can see how little of this core is actually being utilized. This core doesn't seem to have any problem flowing, but even down here you can see that since you have a lot more volume on this side, when it exits this rear core, the airstream seems to be pushed to the left a little bit towards this because there's no real volume coming down here. Now I'm sure you do get some airflow here. I only ran so many particles through here just so you can get a better visual. If you run more particles in this area, it gets to be really convoluted and it's kind of hard to follow these streams. So yes, if I do crank this up, you will see more coming down here. So you are getting some air through here, but you can see there's a pretty significant difference in airflow with these. I think that's just the downside of having this type of tank design and having your cold side come out of here. Out of here. Now let's take a look at the Australian models. This is significantly better than the Night Sports, better than I expected, but I still think there's some to be desired. You can see down here we're still getting more volume on this side because you could see as the air exits the tank, it's still being pushed to this side. So we are getting more volume on this side. And when you zoom into these far ends, we're getting significantly less airflow particles to probably this quarter of the tank. You can see how much more on this side we're getting per channel. Than this far side. And that's, like I said, it was my hunch. It's to be expected. This is definitely a more efficient core, or tank design I should say, than the Night Sports, but I think for the money I would like to utilize the entire core appropriately. You can probably fix this by welding in one of those channels up here like I mentioned in the previous video, but ultimately I think you're still going to run into issues with having your cold side outlet pointed right here. From the top view again, you can see how much more volume you get on this whole part of the core versus down here. That brings us to my design. I chose to use a single large core versus two cores stacked on top of each other like the other U-types. And the first thing you'll notice is why are there so many more particles on the hot side than the cold side? That's because the core I chose has an odd number of cooling channels that the air actually flows through. So the way I designed it is the hot side is going to have fewer cooling channels here, and then it's going to expand into the cold side, which has one more cooling channel. I could have done it either way. I could have made the cold side the smaller side, but I chose to err on the side of thermodynamics. Anytime you have a compression of a fluid, air is a fluid, you're going to heat it up, and then anytime you expand it, it's going to cool down. So I figure this is probably going to be the higher pressure area, and it's going to expand down here in the lower tank and come up to the cold side. The change might be negligible, but that's just something I chose to do. I think this core is overbuilt for my needs. It should be able to handle over 500 horsepower, so this could be good for those single guys. I guess we'll see when I get on the dyno and when I get some actual data coming into this. But you can see from the CFD, I'm getting equal usage out of the entire core. I'm not, only using part of the core like what we saw with the other two designs. Even when you go from the top view, you can see I get real equal airflow throughout both tanks here. And that's exactly what I want. Through all the channels. It's hard to do on two screens. You can see this is pretty good use of the entire core. This is to be expected, and you see this with pretty much all intercoolers, but the main thing is we are using all the channels equally across the entire core. So I'm excited about these results. We won't know until I actually get it in the car, get some numbers and whatnot, but I guess we'll find out soon enough.